I hope you will be lenient to me because last year when I made a talk to PyCon, I said I'm still a Python beginner. And this year, I'm still a beginner. So my progress is very slow when it comes to Python. So please, if you have questions, make sure you know the answer, okay? Okay, so last year I talked about a vegetable and high availability, okay? So this year I'm going to talk about this picture. So can anybody tell me where this picture is from? Very good point. BGs. That's a good answer, but maybe not the correct answer. Beatles. Okay, I hear the Beatles. Okay, what year? 1960s. That's a very good guess. To be exact, 1969. The good year of 1969. And this is from their album Abbey Road. Okay? So it appears we are in the same environment. I can see a lot of experts here, so please help me on this, okay? Because, you know, this is a very complicated topic, and my aim was to simplify it and remove most of the complex stuff so you will not ask your questions. Okay, so I'm not talking about that memory, you know, the Beatles thing. I'm talking about this thing, out of memory, OOM. So this is a simplified picture, but there are many ways to sample your memory. If you're in Linux, you can use top, and there are many utilities out there. If you're in Mac, you can use activity monitor. But there are a lot of columns there, no? So I will just give you one column later that you can zoom in, so you will know that you have a very serious memory problem. So this picture will show you that it's really running out of memory, okay? As you can see, physical memory is 100%, okay? And the very bad thing here is the swapping, okay? So I think the guy tried to fix it, maybe restart the service, so it went down, the physical memory consumption, but after some time, it went back up again. So most probably, there's really something wrong. So this is, you know, what you should be concerned when you see this picture in your system, okay? So why is swapping very bad? So this is a pyramid. You can see as you go to the top, the access time goes down. So it's faster as you go up. And in terms of cost, as you go down, it's less costly. And then if you compare hard disk versus RAM, you can see a big difference, okay? So hard disk access time is 5 millisecond to 20 millisecond compared to main memory or your RAM, 30 nanoseconds to 90 nanoseconds, okay? So that's why you don't want to be swapping, okay? There are many ways to avoid swapping. Like in Linux, you can set a parameter there. I forgot the parameter. We have a lot of Linux guys here like Holden. Something like you set that figure and the OS can, based on that factor or number, the OS can decide how swappy your system will be. So if you put it to 0, most of your stuff will be in memory. If you put it at 1, you know, only in very critical situations it will swap out. Meaning, if you put it at 0 and it will not swap out, what will happen to your application when it runs out of memory? So in Linux, there's a guy called OOM killer. OOM killer will kick in, and based on some computations, it will decide which process to kill, and most probably the highest consumer of the memory will be the one who will be killed. Okay, now so you tell me, Prem, why not use SSD for my swapping? Because, you know, SSD is faster than a hard disk. So let's compare. So for DRAM, that's the throughput, 10 gigabytes per second, and then the latency, access time, around 100 nanosecond. But if you compare it to the, this is 2015, no? SSD, the highest access time or the fastest access time for SSDs, at least for this diagram, is 250 nanosecond. It's still, not close. Okay? But actually for SSDs, it's not more of the access time. It's the performance really suffers when you have smaller blocks. Okay? So the throughput there, which is 6 gigabyte per second, that will drop to around 200 megabytes per second to 1.5 gigabytes per second. And that's too far from the RAM throughput of 10 gigabytes per second. So, like, Rosel, correct me if I'm wrong, this thing is using SSD already, right? Where's Rosel? Yeah, I think I'm using SSD. I think most of us using SSD. But you will notice when your thing is swapping, you will really notice the slowdown, right? And you don't want swapping, even in SSD. Okay, so this is our production problem. This is a snapshot. What happened here is there's a call. Now, right after this call, it's the get device configs. We noticed a sudden peak of memory usage. Now, I will expound later on what type of memory, because if you look at activity monitor in top, there are many columns there, no? Okay. And you will also notice from this diagram that there's a significant increase in the number of objects of type list. So from 24,000 to 13 million. That's already a big flag for you that something is really wrong. Okay? So the way we do it is, okay, Rosel, you deep dive. Okay? So this problem actually is RK here? RK is not here. He saw me yesterday in Starbucks because I was still trying to, really make sure that what I present here is working. But even right now, it's still undergoing pilot testing in some data centers because I'm not 100% sure yet, no? So please bear with me when I present my work around later. Okay, so the flow of this very short presentation would be, I will show you a quick dive of the tools that I use. There are many tools out there, many presentation, PyCon or whatever, Linux conferences, okay? Feel free to, pick your tool, okay? But I think these three will already give you a good picture, okay? So resource, module, Python module, OBJ graph, also Python module, and I think Hippie is also Python module. So I'll give you a quick dive, show some examples in source code, and then I'll also highlight referencing, okay, with how it relates to garbage collection, because that is really what happened to us, okay? And then I present to you a production scenario that we are still debugging right now, and hopefully it's already fixed. And then later I will entertain questions, but make sure you can answer them. Or I would love if you can share your best practice in your company when it comes to dealing with out of memory, okay? Because, we are still, I'm still a beginner when it comes to this. Okay, so let me go back to that, the production problem. That 2 gigabytes, okay, 2 gigabytes memory consumption. This is the call that gave that figure, okay? Resource.getR usage, blah, 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 okay? This is actually just a wrapper for the system's call getR usage. So the who there is R usage underscore self, which limits the sampling of the memory to the process itself. You could also sample the children of the process, or you could sample both the children and the parent. But this one, just the parent. And what I did, that ZenHub thing, that's one of the services that I was trying to deep dive. I limited the workers to 0, so it will not spin children, okay? Children, anyway. I hate children, no. Anyway. Yeah, so, and we are interested, and this is very important, no? Resident set size. The keyword is resident because it's resident in main memory. So this should be what you should be looking for, okay? So again, resident in main memory, because, you know, memory is a very big subject. It could be virtual memory. We are just concerned with this because it's the one that's really in main memory, okay? Now, it's max RSS. The max is just actually a high water mark. Now, it's a high water mark because there are cases when your OS could decide to swap out the memory allocated to your process. And the way it allocates it is it will borrow the memory, so meaning the RSS will now be less than the max. And then when the OS is done, okay, maybe the top priority process is already done consuming the memory, it will return it back to your process. It should never exceed the max, okay? So very straightforward. Always think of max RSS as the amount of memory requested and allocated by your process. So it's a good number to look at. Second tool, OBG graph, okay? So this is a very straightforward example. Number one, we have an empty list. Number two, line number two, we have a list consisting of 3 items. The first item is the empty list. The second item is the list with the empty list. And the third item is the dictionary with a key string X, and the value is the relationship of your objects. This one will allow you to deep dive on your heap memory, okay? So lines 1, 2, 3, that's the heapy stuff, okay? Line number 3 is very important because you don't want to see the heap just before you invoke this line, okay? Line number 4, 5, that's the same example as before. And in line number 6 and 7, we show the heap, okay? So as you can see, in index number 1, this one, there's the list, and the count is 3, as we discussed earlier. And there's the dict, count equals 1 because we only have one dictionary. Very straightforward, but maybe not so straightforward when you see some of our output later. Okay, what I'm doing here is just to check if I was right in saying, you know, in enumerating the list that we created. Okay, so what I did is just to iterate on the index 1. Okay, so as you can see, 3 lists. Okay. Now this one, I'm showing to you how I use heapy to hunt for that object that is the culprit of memory, consuming a lot of memory. Okay, which object is consuming a lot of memory? So lines number 1 to 3, heapy stuff, okay. Line number 4, this class is going to be used in line number 9, which another class, class X, okay. So I'm just trying to show here, you know, referencing, okay, classes using each other. And the important line is line number 12, okay. That line should consume a lot of resident memory, okay. And then lines number 14 and 17, I just instantiate. So I have 2 instantiations. So I generate, I view the heap, and as you can see, it was able to pinpoint that the object that is consuming a lot of memory is of type string, okay? But the next question is, where is this thing from, okay? So heapy also has this call by RCS, and as you can see, it was able to pinpoint that it's in the X class, okay? Now, why is the count 4? Okay, so to answer that, let me show you this graph. So by RCS, it classifies by referrer and by type, okay? Again, by referrer and by type. Now, heapy is actually a product of a master's thesis they have very technical documentation, okay? They really put some computer science stuff on it, no? So you might have a hard time reading their documentation, but there are a lot of examples out there that will show you hints on how you can make use of the calls and then intersect the output so you can find your culprit. Now, the answer for that question, why 4? Because remember, we have 2 instantiations. And as you can see, there's 2 items where the referrer is the X class. So 2 times 2 equals 4. Very straightforward. Now this one, it's a very simple example of, showing you an important concept in Python, which is an object. An object cannot be garbage collected if the references to that object are not yet deleted. Okay? So as long as somebody is still referring to that object, it will not be garbage collected. Now this is one of our big problems because it's a big system. Holden knows about this. And everybody is creating objects, relating objects to each other, and it's very difficult to keep track. Okay? So if you are not the one who is writing that, and we are not the one because we're using an open source framework. So we have a difficult time really, making sure that the stuff can scale. So that is why we have these kind of problems. So what I'm showing here is a simple class. Please notice line number 11, that's a destructor, okay? And the method make underscore foo is just instantiating the class from line number 5. Okay, this one. And then I want you to annotate these lines. Line number 22, let's call it figure A. Line number 25, figure B. And line number 27, figure C. So what I'm trying to do here is show you the references. Okay, so line number 21, FT is a reference to the object that we instantiated in line number 16. Okay? So again, FT is just a reference. The object is really the one that's in line number 16, instantiated line number 16. And then lines number 23 and 24, that's another reference. Okay? So again, we should have 3 references, okay, to the object, the instantiation of the class foo type. So we should be expecting in figure A, that's not line number 22, we should be expecting to see at least 1 reference, FT. In line number 25, we should be, figure B, we should be expecting 3 references now, 1 plus 2. In line number 27, figure C, we should be expecting 2, 3 minus 1, because we deleted this, one of the references. Okay, so showing you the figures, figure A, notice this, 11, okay, that already has 1 reference, and then we add 2, 13, and then we subtracted 1, so that's 12, okay? So the problem is, we started with 11. Now, if even this graph is already, I think I already removed some of the parts, some of the nodes in the graph. So, if you have a big project with a lot of objects, it could be really difficult to keep track of all those references, okay? So this is our production issue, okay? So let me just walk you through very quickly on our thing. We have 3 services, okay? First one is hub. This is a service where everybody goes to for shared stuff, okay? Component modeler, this is the one gathering information about a device or a component of a device so that the collector will know how to monitor or sample the device. This is a monitoring tool, okay? So the workflow goes like this. If you add a device and you want to monitor the device, first you need to model the device. So the component modeler kicks in, gathers information like passwords, usernames, data sources, and all those stuff that's needed by the collector. It passes it to the hub, and then the hub persists that configuration in the database. Now here's the problem that we encounter. When just before collection, just before the performance collector kicks in, it creates a device proxy with the hub. This one, okay, containing all those stuff needed by the collector to be able to monitor correctly the device or the component. Now we put that in the memory for many reasons. Really, number one is speed, okay? And what happened, what I showed you earlier about that sudden peak of memory happens really here in the creation of the device proxy just before collection. And then what we noticed is after the peaking and then after every collection, the memory does not go down. In fact, it goes up. Okay, it's supposed to be, stable. Okay, because nothing is added. But what we notice is something going up. So something is really wrong. And one thing that also compounds the issue is we have a lot of objects. So I am giving you an example here: device, hardware, CPU, and the objects also have relationships with other objects. So a good example here would be a sensor where an endpoint would have many pools, and a pool could have many storage repositories and virtual machines, and a storage repository could be used by 0 or more virtual machines. So you multiply, all those relationships, and you have a very messy relationship. And that's memory footprint, okay? So for every object that you create there and every relationship, that's memory, okay? So again, we go back to the problem. This is the same slide that showed you earlier, okay? And to simplify it, we used Hippie to pinpoint which type of objects are really consuming memory, and indeed we are now very sure that it's the stuff that gets loaded to hub just before collection, as you can see in the sample output. Okay, so the fix. One sentence. Okay, that's the fix. One sentence. Took us. I found some stuff earlier yesterday. Maybe 2 weeks, okay, of deep diving. But outside of that, we have workarounds. So we really spent a lot of time on this thing, okay? So the fix is just to remove unnecessary stuff that is loaded in the hub, okay? Because they're already there, okay? Samples not so much, so we have to experiment and not really deep dive, okay? So the tips I can give you, before I give the tips, let me just show you in code where that thing is really in source code. So this is the stuff that we upload in main memory and send to the hub. So as you can see, there's an iteration there, okay? So imagine every collection, just before every collection, that stuff gets created and never destroyed, never garbage collected, okay? So the memory footprint is really proportional to the number of objects plus, multiplied by the number of relationships, okay? And this stuff also affects the collector because it's here in line number 125, okay? So the simple fix would be remove, okay? So remove it, so now it's very empty. And then as you can see, and we discovered just a few days ago, it's already in the config, okay? Config parameter, this one. So my tips would be, if you are on a large project and you are not the owner of the framework or the project where your thing is based, you need to really deep dive on your data structures before you scale out, okay? The tools that I gave to you, they will give you very good hints, okay, on what your memory footprint would be. And then get in touch with the primary authors. That would simplify your problem solving. And this is a very good tip. This is from our friend, Eric Raymond, the open source guy. Stallman hates him because Stallman hates open source. You have to ask very smart questions to get very smart answers. So my take home would be, again, resource for RSS, main memory, OBJ graph allows you to see your objects, their type, and which objects are consuming a lot of memory. It's already sorted. You can use CP to check your heap. Referencing, it can really go out of proportion, so you have no choice, okay? You really have to deep dive, okay? Especially if it's a big project. And this is I think, where we spent most of our time while we are deep diving the thing, the production workarounds, because the thing is already in production. So 2 things I want to mention. First is you have to accept that there's a leak, okay? There's really something wrong. And then we respond to it by allowing our orchestration to work around the leak. So something like the node should be disposable. So as soon as it is, or just before it reaches OOM, you should already kill the node, okay? Because you don't want the OOM killer to kick in. Because when it kicks in, it could kill, one of your very important processes. So just before OOM kicks in, you should be able to dispose the node and maybe boot another one. So your orchestration should be very fast, okay? So that's number 1 thing that we did. Number 2 is we also shard the monitoring workload or whatever workload you have. And then we really compute, okay? Sharding based on the number that can, we compute so that we have enough memory that can accommodate that number, and then we don't reach OOM, okay? And then we use the orchestrator to, compute how much memory a node should get, okay, based on these equations, which is objects times relationships equals the memory footprint, or directly proportional to the memory footprint.